We have another problem here that will be solved using the Bernoulli's equation. So the problem goes like this. You have a medical technician and is trying to determine what percent of a patient's artery is blocked by the plaque. To do this, she measures the blood pressure just before the region of blockage and finds that it is 1.20 times 10 to the 4 pascals, while in the region of blockage, it is at 1.15 times 10 to the 4 pascals. Furthermore, she knows that the blood flowing through the normal artery just before the point of blockage is traveling at 30 centimeters per second, and also that the specific gravity of the patient's blood is 1.06. The question is, what percent of the cross-sectional area of the patient's artery is blocked by the plaque? So to solve this one, the first thing that you should note on the problem is you're actually given the specific gravity of the patient's blood. This is very important in the development of the solution. And also, yeah, you should note that what is asked is actually the blockage, the percentage of the cross-sectional area that is blocked by the patient, but that is blocked on the patient by the plaque build up on that. So to do that, let us try to illustrate this problem first. Let's try to illustrate that. So if you have a artery like this one, so the problem says that just before the blockage, so we assume that there is a build up of, say, something here. This is the normal cross-sectional area of the artery, and then this portion here, which I shaded, is the blockage, and um, this is now the new cross-sectional area with which the blood is flowing. So it's stated in the problem that just before the blockage, the pressure there, meaning this portion here, I will label this as region 1, and the portion of blockage, I will label that as, or I will set that as region 2. Okay, it's stated in the problem that the pressure just before the blockage, meaning the pressure at 1, is given to be 1.20 times 10 to the 4 pascals. And another is on the point of blockage. So as you can see in this portion here, it is at P2 1.15 times 10 to the 4 pascals. It's also stated in the problem that the velocity with which the blood is flowing is given to be 30 centimeters per second. So this 30 centimeters per second, this is the velocity of the blood before the region 2 or the point of blockage. So since this is not an SI, I will just convert that first, 30 centimeters per second to SI units. Thus, I know that in 1 meter, I have 100 centimeters. So I will now have, okay, I will divide 30 by 100. So I will move 2 decimal places to the left. So I will have 0.30 meters per second. Now this is the velocity of the blood in SI just before the point of blockage. Okay, now from the problem, I have mentioned earlier that it's very important to note the specific gravity that is given in the problem. So we know that specific gravity is just equal to the density of the substance in question divided by the base nemo, which is the density of your water. So the density of the substance in question in this case is your blood. So the density of, I'll put it B, now referring to the blood, divided by the density of the water, and that is given in the problem to have a value of 1.06. Okay, why this is significant? Because from this expression, this implies then that the density of the patient's blood is equal to 1.06 that of the density of water. Okay. And you know where the density of water, you know that to have a density of 1000 kilograms per cubic meters. Okay, so you label that as equation 1. So this portion here, you call that as your equation 1 because you are going to use this later. Equation 1. Now, the next thing is you remember from continuity equation, since you want to know the velocity at point 2 here, at the point of blockage. So how do you get that? You recall from the continuity equation that uh, you have A1 V1 is equal to A2 V2. Okay? So what you are going to do is you find an expression for V2. So you have V2 is equal to A1 V1 all over A2. Take note that you don't know yet these values. A1 and A2, you don't know this value. So you could not just simply use that equation because you have two unknowns there. So you label that as your equation 2. Okay, now the third thing, since this is a Bernoulli problem, we are going to write or set up our Bernoulli equation. So our Bernoulli equation is simply given by, okay, when you set up the Bernoulli equation, I think you can remember this one. You have P1, no, let's have the general equation first. You have P plus 1 half rho V squared, and then you add rho GH is equal to a constant. What that means is that you can actually expound that one. You have P1 plus 1 half rho 1 V2 plus rho GH1 is still sub 1 is equal to P2 plus 1 half of rho 2 V2 squared. I forgot to put one subscript there. Plus rho 2 GH2. Okay, but you need to recall that the expressions that you find na ay mga rho, okay, kining rho 1 o rho 2, these terms rho 1 and rho 2 is actually the same. Since our assumption when we are working with Bernoulli and continuity is we are working with incompressible fluid. Therefore, that means that the blood that passes through this cross-sectional area and the smaller cross-sectional area actually retains its density. So for brevity, P1 and P2, I will set that to be just equal to rho. Okay, from this expression then, you will have P1. This is pretty boring. That P1 rho V1 squared and plus rho GH1 is equal to P2 plus 1 half of just rho V2 squared plus rho GH2. Now, take note that our problem asks us to find for the percentage of the cross-sectional area of the patient's artery in the that is blocked by the plaque. But before we can solve for that, what we can do instead is to find for the A2 katong cross-sectional area sa giagian sa imong blood. Karon mao na atong masolbad una. But as you notice in your Bernoulli equation, wala kay nakita nga expression for A2 ana. But you need not to worry because this V2 term that you see here would actually be replaced by equation 2 above. If you do that, you will now have A2, which is what you desire in this case. So let's try to substitute that in the equation. So we have P1 plus 1 half rho V1 squared plus rho GH1 equal to P2 plus 1 half rho, and then substitute equation 2 here. So you have that is just A1 V1 all over A2 quantity squared plus rho GH2. Now, what I am going to do next is I want to isolate the term that contains the A2, which is what I desire to solve. I want to isolate this one, so the easiest step to do that is to transpose these two terms to the left-hand side. And when I do that, I will have P1 plus 1 half rho B1 squared plus rho GH1 minus P2, and this one minus rho GH2. And what is left is the isolated term 1 half rho. I have A1 B1 over A2 quantity squared. Okay, so after that is I will be combining like terms. I will combine P1 and P2. So I will have P1 minus P2. And then this, since this is a lone term, it doesn't have a similar term. So I'll just copy that. 1 half rho P1 squared. And then these two terms has actually a common term, which is this portion, this rho and G. Rho and G. So what I'm going to do is to factor out rho and G. So what is left is H1 minus H2, because this is negative here. So is equal to 1 half rho. I will just distribute the square. I will have A1 squared B1 squared all over A2 squared. Now, take note in our problem, or in the general derivation of the Bernoulli equation, we actually have this illustration, if you can remember. Like this one, you have cross-sectional area 1 here and area 1 here. And the height h then is from this, divided this 1 as 2, 1 and 2. That is your height h. But take note that you don't have any height h involved in this problem because of the assumption that your artery is just straight line, meaning h1 and h2 lies on the same reference line. Therefore, it doesn't have any height. So h1 and h2 is just 0. So that is very helpful in reducing your equation. Since that is just 0, so what is left is this expression, P1 minus P2 plus 1 half rho B1 squared is equal to 1 half 1 over 2. We have A squared here, and then the numerator will be rho A1 squared B1 squared. So let's continue with this one. So take note that our goal is just to find for A2. So what I am going to do in that case is to multiply both sides of the equation by a factor or a term with which I could actually isolate this one. But I think that will not be practical in this case. So what I am going to do first, our goal is to find for A2, the one that I shade here. So what I am going to do is I will cross this over there. So I will now have only the A2 term. I will retain the 2 on the denominator. So when I do that, I will have A squared, and then you multiply by P1 plus P2. You have a grouping symbol here. P1 plus P2 plus 1 half rho B1 squared, okay, is equal to what is left on the right hand side is rho A1 squared B1 squared over 2. Okay, and the next thing is I want to isolate A2 because that is what I want, or that is what is asked in the problem. So what I'm going to do is to multiply both sides by this entire term that you see here, multiplied by P1 plus P2 plus 1 half rho B1 squared. So that is what I'm going to multiply to the both sides of the equation. So what happens on the left hand side is that this term that is beside A2 will cancel out, and then what is left then is I will multiply it here, this whole term with the term on the right hand side. So that will simplify our equation. We will have A2 is equal to, copy the numerator, rho A1 squared B1 squared everything is then divided by 2 and multiply that with P1 plus P2, P1 plus P2, and then plus 1/2 rho. Okay, let me just check. Okay, that's right. 1/2 rho V1 squared. That is what is left of the problem. I mean of the equation when we try to multiply both sides by 1 over P1 plus P2 plus 1/2 rho V1 squared. Okay, so this is looking good. And the next thing that we are going to do in this case is to recall this from our algebra, this law of radical. If you have the nth root of, say, a to the n times b, you could actually take out this term that has the same power with the index of the radicand. So that means that will reduce to a and then multiplied by the nth root of b. So that is what we are going in the case of a1 here. Because why we are going to do that, we want to have a comparison between a2 and a1, and we know that it doesn't have numerical value in the problem. So ato na i-compare mo nang ato siyang pagawason. So when I apply that law of radical that I have cited earlier, I will take the square root first on both sides. And when I do that, I will have now a2 is equal to, so I will isolate a1 in that case. a1, and then the square root of, I will retain everything here, rho, and then I have b1 squared all over 2 multiplied by this term, b1 plus b2, b1 plus b2 plus 1/2 rho b1, and that is squared. Okay, you have this expression now. The next thing that you are going to do is to simply plug in the values. So you have a1. So you cannot do something on a1 because you don't have any numerical value for that. But you know, for density, that is density of blood, that is 1.06 times the density of water, 1 times 10 to the 3 kilogram per cubic meter. Now you might be wondering, why did I express the density of blood in this way? Because of the fact that what is given in the problem is the specific gravity. Kaya nagkaroon tayo ng expression. And V1 is 0.3 meters per second. That is squared. Divided by the denominator, which is 2, multiplied by P1, the pressure before the blockage, and that is 1.20 times 10 to the 4 pascals. So this is a nice problem because it is given in pascals. We don't have to convert everything because if it's in atmosphere, then that is, you have to convert that into Pascal. So luckily, it's not the case here. Okay, so let me just check why I have plus. So I actually committed a mistake here, and I noticed it late. This should be minus P1 minus P2. So this one also will be P1 minus P2. Sorry for that. P1 minus P2. Okay, so this one will also be P1 minus P2. Okay, so we have corrected that one, so we will just put 1.15 times 10 to the 4 pascals. Okay, pascals, that plus 1/2 of rho, which is 1.06 times 1 times 10 to the 3 kilograms per cubic meters m3, multiplied by V1 squared, which is 0.3 meters per second, then you square that one. Everything in this term is under the radical sign. Okay, now the next step that we are going to do is to check the units. Let's try to check the units if we will get a sensible result out of it. So let's disregard first the numerical value. So I'm working with units. I have kilograms per cubic meters, and then you multiply it by meter per second squared. I mean the meter squared per second squared, sorry. And then you divide that with Pascal. So you know from the previous lectures that Pascal is just kilogram in SI per meters times second squared. That is your Pascal. So this one here is just Pascal, so it's just equivalent to this one. Plus, this term is, you have kilogram per cubic meters, and then you multiply it by meters squared per second squared. So when you do that, take note, what will happen is on the numerator, m cube, m squared over m cube, so the m squared will cancel out, but this remaining is just m. Therefore, the numerator is just kilogram meters, kilogram per meter second squared. On the denominator, the same thing happened with this one, m squared m cubed, so only one m is retained in the denominator. So this will just reduce to kilogram per meter second squared, which is, or which should be in the first place, the same with this one. So since you have the same unit, so you just copy the unit, kilogram per meter second squared. And then when you do that, that will just cancel out. Okay, and that is very important that it should cancel out because in the first place, we are doing comparison on the value of A1 and A2. So we want a rate or a percentage. So we cannot have a percentage that has a unit. If along your problem, along the solution, you actually have a unit here, and that is trying to tell you that you actually have a problem with your equation that we are working with. Okay, so this is a good sign because we don't want any unit for a rate. Okay, so from that, we are going to work with our calculators in this case and try to find the value that we can arrive. So A2 then is just, okay, let's work with the values on our calculator. So A2 then is given by A1, and then the term on that will be plugged into your calculator. So the whole magnitude of these values that you have under the radical sign will give you 0.29, 0.2951 with no units. So when you try to round it off to 2 decimal places, that will just be A1 of 0.30. But this is not what is asked. This is not what is asked of you from the problem. What you are getting instead is, if we go back to the illustration, so what you actually get from your solution is you have A2 is given by 0.30 of A1, or that is trying to tell you that the A2, the small cross-sectional area, is just 30% of the original cross-sectional area A1 of your artery. But since the problem asks you of the percentage of the cross-sectional area that is blocked by the plaque, that is trying to say that the cross-sectional area, aside from this small hole with which your blood is flowing, katong itabunan yun sa plaque, which is this one. And that is not 30%, but the complement of 30% or 70%. 70% is actually blocked. Is blocked by the plaque. So that is how you solve this problem, by the plaque. Okay, so 70% is blocked by the plaque. So that means this portion are blocked by the plaque. So what you are able to solve instead is A2. meaning that is that's the new opening on the cross-sectional area, which is just 30% of the original cross-sectional area. So since the problem asks you how much is plaque, so that means that the closed portion, which is 70%, is what is plaque by the plaque.